Okay, I guess you can see my slides.
Yes, looks good.
Okay, so welcome everyone to this DVCon. So we have, Andy and myself, so I'm Youcef, and with Andy, we are going to present you how you can find hidden bugs in deep cycles using advanced debug methodologies for software-first system validation. So today you are getting a design much bigger, and they have to be validated with software which is also bigger. I mean, you have software stack that you have to enable with your design. And for that, you have to run hundreds of billions of cycles in order to find issues and, of course, debug them. On top of that, we have teams who are willing to adopt software-first validation strategy, which makes you have to get emulation and prototyping platforms very efficient and powerful in terms of debug technologies. So here with Andy, we are going to show you how using a multiprocessor design case study, we are finding bugs on very deep cycles using our latest emulator and FPGA prototyping systems. So that you can, of course, enable your software-first system validation. I will present you the part with ZeBu, so it's going to be the part 1, and Andy will present you the second part, which is using HAPS 100 FPGA prototyping. So why software first? Previously, you were probably running emulation on systems like this one, where you were using, you were having, I would say, some initiators like CPU, GPU, image signal processing, connected to some peripherals using some network on chip. And with that, you had some transactors and some tests. So the focus was really about the DUT itself. And the test part was very small. But you were still able to run some tests on millions of cycles. And for that, you were able to use something like one unit ZS4, which is our ZeBu server 4. But today, your designs are getting much bigger, right? And with that, you are also using your full software stack. So in order to find bugs, you need all this software. So you need a complete system. And with that, you are running much longer tests with much more activity in your design and, of course, in your software. So everything is getting bigger. And of course, for that, you will be using more ZS4 systems. So now let's see, for this very big system, as a high level, how you usually debug. So first of all, you run your billions of cycles. Thanks to signal monitoring, you can reduce the window of debug, so to some millions of cycles. And then again, thanks to your checkers, monitors, you can reduce again the window of debug. Then with that window, you can root cause your issue in terms of cycle and gate here to you can root cause everything thanks to waveform debug. So for that, you will be using signals monitoring, checkers, system Verilog assertions, or whatever assertions you have. You will get waveforms of your key signals, and of course, full visibility of your design, thanks to waveforms. Now, in terms of ZeBu technologies, so we have our monitors, checkers, and stimuli. So we have customers, probably you, who are running emulation for days and weeks. So one single test running days and weeks, and you need to isolate a window of debug. So if you start with a system like that, basically you need to specify the interfaces, the signals that you want to monitor. And then with the test bench, I mean, the software stack and the transactors, we are recording everything that is coming to the DUT. So thanks to that, if you have some non-determinism due to your software, thanks to the fact that we record that, we will be able to replay that. So basically what is happening in our technology, with our technologies, is that we are enabling our monitors and checkers during all the run. We are saving the stimuli. So everything that you are sending to the DUT, we are saving that. And also we are saving the DUT state. So we can save the DUT state whenever we want. So that when you have an issue that you are observing after a few weeks, for example, or even a few days, you do not need to restart everything from zero. I mean, the run from zero. You can just restore a hardware state and replay the stimuli from there. And then you can capture a waveform. So when we capture a waveform with our technology, then we run waveform expansion. Excuse me. So with our system, we have a high-speed interface between our emulator system and our host PC that controls the emulator. So thanks to that, we can capture raw data on the disk using Verdi. So we have two ways to run emulation, two main ways, I would say, to run emulation. So either with Verdi or with ZRCI, which is UCLI based. So with Verdi, you can capture this raw data here, and then you can run waveform expansion. So two possibilities. Either you do that in batch mode, or you do that interactively. So interactively, basically, you will run Verdi directly on that ZTDB, and Verdi will compute every signal you have in your design when you do a drag and drop. So for example, for a 2.5 billion gates design with a waveform window of about 500K cycles, each drag and drop from the RTL source code to the waveform will be done in less than 1 second. When you do waveform expansion in batch mode, and then here we will generate waveform in a new format, which is our native ZeBu format here. And that one is very efficient to display any signals. So all these waveform expansion engine and Verdi is scalable for huge design, for big designs, and also for big waveforms. So we were saying that, yes, with Verdi, you can run emulation. So this is how the GUI of Verdi is looking like when you run emulation. So you still have access to the DUT hierarchy, the signals, the RTL source code. Here you have some buttons that are dedicated to emulation. So basically here you can control the runs, the run in terms of cycles or time. This is the same here, but here you will have more clocks if your design has more primary clocks. Okay, so you will be able to free or control the clocks individually. Here we have some buttons like here, the sniffer, which is the technology used to capture the stimuli and the hardware states. Then we have the triggers, the system verilog assertions. Here we have also a GUI for the waveform capture, to capture signals or to capture all the design in raw format. And here you can also select any register of your design, do a drag and drop to that watch pane. So during the run, when you stop the run, you can directly see the values updated here. And here you have a console where you could source any UCLI file to, for example, apply a set of forces or preload some memories. So you can do everything also with the ZRCI console. Now our case study. Here we have created a system on chip, an SoC with a lot of RISC-V processors. And each RISC-V processor is made of 4 Rocket cores. So we have a kind of network on chip and some peripherals. And the peripherals are connected to transactors. And we have our application like that is running. So what we are doing on our RISC-V processor, for each processor, we will place our monitors, which is called ZDPI. So that is our technology that will allow us to capture every single interface of our RISC-V processors. And here for each Rocket core, we will also capture their interfaces. So all this is done with our ZDPI technology, which is our high-speed monitor technology. Here now, between the software parts, so everything that the software sends to the DUT, we will be able to capture that thanks to our sniffer. So anything you do, you preload a memory, you force a signal, you drive a signal, a transactor sends some data to the DUT anywhere, we will save that so that we will be able to replay it. Now here we have our fast readback technology, which allows you to get full visibility. Fast readback is a new technology. Until today, and still tomorrow, you will still have this readback technology, but with fast readback with a very limited additional instrumentation to the DUT, we will be able to capture waveforms much faster. By much faster, I mean we can go up to 30 to 50x faster than the regular readback. And so that will give you full visibility. Excuse me. So now let's see what is happening with our design when we run the test. So we are running tests for millions, billions of cycles here. We are using the sniffer technology to save the hardware state and the stimuli. So between each hardware state and between the two hardware states, I would say here, for one hardware state and the stimuli saved after that, we call that a sniffer frame. So we will be capturing several sniffer frames during all the run. And in parallel to the sniffer frames that we are capturing, we are capturing the interfaces of our RISC-V processors and Rocket cores thanks to the ZDPI. So everything will be streamed out the emulator and saved in ZTDB directories. ZTDB directory. So then after some point, we see a failure. And thanks to the logs of our monitors, we are able to define a window of debug. And then we are restoring that hardware state, which is done before the window of debug. We are able to restore it, replay the stimuli, so that thanks to the full visibility, we are getting a waveform for our window of interest. When the waveform is available in raw format, then we can run offline or interactive waveform extension and debug with Verdi. So our log looks like that. So each RISC-V processor here is booting Linux individually. So what we have observed is that we have during our run is that one of the RISC-V processor is not booting Linux correctly. It looks like it is hanging. So what we are doing is that we are checking the cycles that we are getting here thanks to our monitors. And Because here we know which RISC-V processor is hanging, we are processing the monitors, I mean, the data we have been streaming out for that processor. So each core here had some data that we have saved in a ZeBu. So we are now processing them, and for each interface, we have the log, and then we realize that we have one of the core here, which itself is hanging. So the main hang of the RISC-V is due to one specific core at one specific cycle here. So the symptom, I mean, the last message displayed here is in fact good, but the next one not being displayed allows us to come closer to the real issue. So we know the real issue is happening just after that cycle here. So in one run here, we are able to define a window because we know we will debug around that cycle. So now using our fast readback technology, we are replaying the stimuli. And from the cycle of failure that we have observed, we will be able to restore the hardware state, replay the stimuli, save a waveform in a ZeBu format of all the design. And then we are running waveform expansion and debug with Verdi. So I'm going to be a bit fast, but here, this is the kind of waveform you can get with Verdi. So of course, you will have your regular waveform, your signals here, but here we are providing you additional information. These are what we call the reason codes. They help you understand how these values are provided to you. Basically, you can see some NC, some X's that could look strange, but as a summary here, when a signal is dumped, that means that the value is taken directly from the emulator. Computed, that means that we are simulating the value with our waveform expansion engine based on all the signals that are captured from the emulator. Mixed here, this is for a vector. So if you expand the vector, you will see the reason code for each bit you have here. Constant one, that means that your design had some signals that were not driven. And in that case, we are driving them automatically to 0. And that 0 can then be propagated through some other signals. So we will optimize the other signals, like if you have a reset active low and the reset is connected to GND, then the reset will be propagated and some logic will be removed, and all these registers will get a constant reason code. Optimized here with NC, so not computed. That means that you had at some point a signal that is loadless. So it is not driving anything. And we have to remove this useless logic. So we remove this useless logic so that you can get more data on your emulator, more DUT logic in the emulator. Or you could also save more hardware modules in the emulator. Excuse me. So the loop here, when it is 1, it is because you have a loop in your design that is stable. But when we put an X here, that means that the loop will be oscillating. So we are letting you know that you may have some non-determinism inside your design. Okay, and here with computed, here we are just showing you that while we are just propagating the 0, 1 from the signals, or X here from the loops, and NC from optimized signals. So these computed, of course, is the output correspond to the output of combinational signal, and that waveform is something I had created. I mean, I created a small design just to show you the strangest waveform you could see, but that is to allow you to know that you may have some non-determinism here. You have some signals that are useless, so you may check if that is expected or not. So I'm going to be a bit fast because I'm late, I think. So here, this is how we are instrumenting our fast readback technology. So with some dumb vars, you specify the scope on which you want to apply QAWC. That file, you give it to VCS with all your duty, of course, to get it taken into account during elaboration. That VCS script is given to our Youcef script so that you compile your design and have all the database ready for emulation. So here you are giving the script, you are giving the architecture file, which is somehow kind of description of your emulation system. And here some debug commands to enable some debug technologies. So this is for our latest sniffer technology, so to capture the stimuli and replay them. And this is to enable our fast readback technology. This is a summary, I would say, of UCLI command to make a run. So this directory starts ZeBu and followed by a directory. That directory will contain everything you capture from the emulator. Sniffers auto-create 2000 seconds. That means that we will save a hardware state here every 2000 seconds. C-call here, we are specifying where we will be saving all our monitor data in raw format. We're running emulation, and then we stop everything. So that was in the main run. Then when we are processing the monitors and we want to replay the stimuli and capture a waveform, we will load, I would say, our previously saved emulation database where we have the sniffer frames. So then we can restore the system at a specific cycle and then capture a waveform using these dumb commands. And then we replay the stimuli with a replay command. So shortly, ZRCI main run, we do the first run. With the ZDPI report, we are post-processing our ZDPI that data with our C function here. So then we can here have in our logs the information that we need, like the failure of cycles, and determine a window debug. Here we replay the stimuli. We capture a ZTDB here, and then with SimZilla, we are running waveform expansion here in batch mode. So we are getting a waveform here that Verdi can directly take as input and display the waveforms with the RTL source code. And then, of course, you can go ahead and debug. So this is how we have done with our multi-risk 5 system. So I'm going to give the hand to Andy for the next step. If you give me 1 second. I cannot find Andy.
Hi, Youcef. This is Aiden. It looks like we lost Andy.
Yes. Can we then replay the video maybe for his part?
Yes, just give me 1 second. Do you know at what time his part begins?
It should be around 20 minutes.
20 minutes, okay. Let's see.
Yes.
Okay, I think I found it. Does that look correct, Youcef?
Yes, yes.
Okay, perfect.
Thank you.
FPGA prototyping system. Initially, I'll provide an overview of how the latest FPGA prototyping system, such as HAPS, with its enhanced debug technologies, has enabled extended deployment across the complete verification spectrum, from initial RTL debugging through to system-level performance analysis. Moving on to the RISC-V based processor SoC debug challenge. First of all, I will demonstrate how we can prepare the SoC for effective FPGA-based prototyping at the highest possible speed and with a maximum debug visibility scope. I will then demonstrate how we can locate the point of failure from an initial run and then set up the debug technologies for a subsequent run to capture the maximum debug visibility around a point of failure for offline debugging in the Verdi environment. The widening scope of FPGA prototyping means that it's now deployed at multiple points in IP and SoC verification. From early RTL debugging, hardware and software validation, to SoC performance modeling, and everything in between. The increasing scope of deployment demands that FPGA prototyping systems have some primary requirements. High performance is always important to increase the number of verification cycles that can be completed in a given time. Some of the hardest to find bugs only become evident over petacycles of operation. It is important that we have a way to get to those points of interest which might not be feasible using simulation or even emulation. High capacity and scalability is also important as IPs and SoCs are only increasing in size. The need is always to be able to implement, bring up and operate the most complex IP or largest SoC in a given time. Flexibility is equally important to continuously repurpose available FPGA prototyping capacities for the specific need. It could be multiple implementations of a given IP running independently and in parallel for short times to the largest SoC running across multiple systems for multiple days. And of course, all of this is only useful if we can get the necessary visibility into the DUT, with different capture and resolution requirements depending on the specific debug or observation need. FPGA prototyping systems also offer multiple verification opportunities due to the availability of physical interfaces that are either built into the prototyping system .
Hi, Andy. This is Aiden. I started playing the video if you would like to start where we left off.
Yeah, can you hear me?
Yes.
I apologize. I had a power outage here.
Oh, no problem at all.
Yeah, so if you could put me back onto, I can't see the screen.
Yeah. Or you
Okay.
want to share, or you want me to share and give you control?
Can you pass it to me?
Yes.
Okay, let me just. Okay. Okay, I apologize everybody. I had a power outage here, but I'm back now. Okay, so thank you, Youcef, for the first part of this presentation. For the second part of this tutorial, I would like to illustrate how we could debug the same RISC-V based processor SoC using the Synopsys HAPS 100 FPGA-based prototyping system. Initially, I want to provide an overview of how the latest FPGA prototyping technologies, such as the HAPS 100, with its enhanced debug technologies, has enabled deployment across the complete verification spectrum, from initial RTL debugging all the way through to system-level performance analysis. Then moving on to the RISC-V based processor debug challenge, I want to first demonstrate how we can prepare that SoC for effective FPGA-based prototyping at the highest possible speed and with a maximum debug visibility scope. I'll then demonstrate how we can look to locate the point of failure from an initial run, and then how we can set up the debug technologies for a subsequent run to capture the maximum debug visibility around the point of failure. Okay, so the widening scope. Sorry, let's go back one.
Can you ask control or remote control? Hold on. Okay,
It'd
so
be
you should
sent to
have
him remote
control.
control.
Yes,
Okay, I have it
you should
here.
have control out.
Okay. Okay, so the landscape of high performance FPGA prototyping has changed in recent times. As I say, the enhanced features, the increased debug visibility, it means that FPGA prototyping is now being deployed across the whole verification spectrum, from early RTL debugging through to SoC performance analysis and everything in between. Primary requirements for FPGA prototyping is always high performance. We want to be able to run, okay, the most complex IP and SOCs over petacycles of verification coverage. And we want to run these for days, for weeks. And obviously, if we can run them at the highest possible speed, we can get to the point of interest and we can improve the coverage over a period of time. Also, high capacity. We want to be using the largest systems that can be scalable and flexible. Obviously, IP and SoCs are always growing. Okay, so we want to be able to accommodate all of those or multiple items on each of these systems, right? And to to run at the highest possible performance with the highest level of debug. The HAPS systems are also scalable, as we'll see, so we can actually cascade this together to create some very large prototyping environments. I also say visibility capabilities have become very important. We want to be able to see what's going on within the DUP. Obviously, we want to be able to collect high capacity debug visibility at speed. We want to be able to capture the platform operation. We want to create databases that we can use offline for verification in the debugging in the Verdi debug environment. So all in all, what we have here is flexibility to help locate the hardest to find bugs. The wider scope, as I say, for FPGA prototyping, the ability to have real-world I/O. So let's go back one.
No, sorry, that's my bad.
Is that you?
Yeah, I was admitting someone to Zoom.
Oh, okay. Let's go back a couple of slides. Okay. As I say, the wider scope of verification is enabled by the flexibility and capability of the FPGA prototyping platforms. Certainly, the ability to accommodate real-world interfaces for interface validation. We might be wanting to add daughter cards along with designware IP for PCI Express or HDMI validation. We might also want to have links to software debuggers to improve on the software development. Okay. Also, transactors are used throughout on the platform. They're used to actually upload and download large capacity data for stimulus or for debug capture. Also for hybrid prototyping, where we'd want to use a virtual platform running C models in conjunction with items running on the FPGA prototyping platform. And also the deployment of speed adapters. This could be so that we can actually connect to real world endpoints or root complexes. It could be PCI Gen 6. So yeah, it would look like a real device from the prototyping standpoint. Okay, so just a bit more about the HAPS 100. This is our latest FPGA prototyping system. It's got the highest performance and it's the most scalable system that we've created to date. We can actually cascade a large number of these to actually give us up to 1 billion gates of capacity, running, from 10 megahertz when we actually have an SoC, partitioned across multiple FPGAs and multiple platforms as well. So when developing this system, debug capabilities was a primary requirement. We want to be able to debug at the highest level of performance and to obtain the greatest possible capacity. And it might well be that we want to run these for days on end, and then we might want to actually slow it down in order to actually capture large amounts of data for offline debugging. These systems are architected. We also have dedicated debug circuits and memory modules. What this means is that we have companion devices sitting alongside the user FPGAs, so that there's minimal intrusion to the DUT itself. It means that we can actually collect the debug at high speed and at high capacity, and we can read it off the platforms and seamlessly join it together to give an SoC level representation. We also have some high-speed host interfaces to the host PC itself. This could be USB 3 or QSFP. Again, we want maximum possible speed to actually extract, high-capacity data off and on the platform. It's also been designed for use on data centers, but it can also be used on desktops in lab environments. We know that FPGA prototyping systems appear everywhere, depending on the verification challenge. But these in particular, they are designed to sit in 19-inch racks with all the mechanicals required and all the power supplies to make the installation straightforward and operational. In terms of debug, the latest HAPS 100 platform has got multiple debug or visibility options. All of these, they have a trade-off in terms of performance, intrusion to the DUT, okay, and also the capacity. So what we have here on the right-hand side is really a visual, okay, of the trade-offs in terms of system frequency and also sample length signal count. Starting at the bottom, the fastest possible debug mechanism is actually to use the resources of the user FPGA. So this is what we call on-chip FPGA debug. It will work in conjunction with the actual DUT itself, and we can actually operate at the highest possible speed. There's no interfaces to any external devices, and we can catch that, and then we can download it for offline debugging. Going up a bit, we have the deep trace debug. This is using the companion circuits that operate in conjunction with the user FPGAs. Here we can capture large amounts of data, okay, and these are from the single or multiple FPGAs. And at the top, we have a new technology which we call global state visibility, and this is really where we can actually stop the platform. We can actually collect the full states of that platform. We can step it, we can capture it again. And from this, we can create very large databases. It could be hundreds of thousands of cycles that, again, can be offloaded the platform and read into the Verdi environment, as I say, for debug purposes. And the great thing about all these different debug techniques is that they can be used in conjunction with each other. We can accelerate to a point of interest. We can use the fastest on-chip debug capabilities to search for a pre-event. We could then slow it down, okay, to capture more visibility using the deep trace debug. And then, as I say, when we capture a very interesting trigger point, we can then step into global state visibility to actually stop, capture, step over hundreds of thousands of cycles. So, okay, if we look at the RISC-V based processor SoC, the example that Youcef was talking about, what this is a RISC-V architecture, 4-core processors. What we know here is the Linux boot routine. It could take over a billion cycles to complete. What we do know is that it's actually locking within that Linux boot routine. So in this case, what we will attempt to do is to take a single instance of this. Okay, we'll look to see if we can implement it into a single FPGA to maximize the system performance. What we do know after some initial studies that we could accommodate this in a single FPGA. The caveat here is actually the RAM to hold the boot code is too large for the FPGA itself. So we'd be looking to use external daughter card to hold the boot code to stimulate the DUT and then to actually capture some activity. So what we're looking for here is a standalone DUT. We want to self-stimulate it from the boot code. We might want to monitor the UI output and that can be on a real-world host, or it could be via transactors. And then we want to enable the debug to detect and capture the activity. Okay. A typical technique in FPGA prototyping is to actually create an infrastructure that sits around the DUT that will help us with the prototyping, just the prototyping environment, okay, for this DUT. And what we have in the toolset is a range of transactors, daughter cards. We've got some interconnect modules that can be, put together to create this this prototyping infrastructure, as we call it. So in the case of the Rocket IO, what we do know, as I said before, is that the boot code will have to be uploaded and held on an external daughter board for the capacity. We can do that via a range of transactors through the what we call the UMR bus. This is a high performance bus that connects from the host PC to the DUT. Okay, and the motivation here is that we will upload the boot codes to the DDR daughter board. We will then release the reset of the DUT and allow it to access that boot code in order to stimulate itself and to to get to the point of interest. We can also monitor the UART. In this case, we're going to use a real-world GPIO board that can connect into the host PC. And what we do know is that we can put this all together, and we won't compromise on the performance. We can actually clock it at high rates. And after some initial studies and putting this together, we know that we can actually run it at 100 megahertz, okay, and without compromising the performance to collect the data. So after putting that together, we will now go forward, and we're going to actually enable the debug technologies. And in this case, we're actually going to do everything. We're going to enable everything. So in the first instance, we're going to enable the on-chip FPGA VRAM and the off-chip, the DTD deep trace debug, okay, to capture AXI traffic between the DUT and the memory, or between the Rocket IO, okay, and the memory. Really across all of the AXI buses to start with. And for this, we can actually make use of the dump bars that are resident in the RTL that are used for simulation and for emulation. We can use those as trigger scenarios. And then quite simply, we add a very simple file or a script just to actually define the depth of each of the debug technologies, the sample clocks, okay, whether we want state machine based event capture, okay, or even how deep it will be, and there's a few other advanced features as well. We can have it as always armed or qualified sampling. So we add some scripts into the implementation flow. We run it through. We look at the instrumentation log after the partition step. This is before we go to synthesis and place and route. And what we see here on the right side at the bottom, we can see that we can capture the signals that we want without compromising on the performance. That is, the sample frequency of the debug technology is not compromising on the performance estimate of the DUT itself. Next step is to enable the global state visibility. As I say, this is the ability to actually run the platform to a specific point. We can use it in a synchronous mode, which means that all of the FPGAs on the prototyping cluster can be stopped, and we can grab the states of each of these FPGAs and each of the systems. We can read it off, and we can synchronize it so it appears as a, as I said, transparent environment, okay, of the actual DUT operation. So say in this case, we can set it up in a synchronous mode. We can set it up so that we can capture very large amounts of data. As I say, 100,000 cycles can be captured in an hour. Okay, and what the tool will do here, okay, in order to manage it, it will actually insert a clock control module to manage the stopping and stepping of the DUT. Okay, obviously we have to make some consideration to the clocks that we can stop and step. Obviously, if it's a DDR module, we might not want to stop that because there are concepts of reset cycles. Okay, but we can actually manage the clocking of the DUTs, okay, to make sure we can control it. So once we've enabled it, we've put together the infrastructure. Okay, we've done some tests. We are able to implement it and enable the debug. We actually run it on the platform. We upload the boot code to the external DDR device via the transactors, something that we call the backdoor approach. We actually then release the reset to the Rocket system, okay, so that it can go and collect the boot code and actually start the execution. Now what we can do is we actually monitor it on the UI output, and then quite simply what we see is it appears to lock, okay, at the cycle that I list here from reset. Now running at 100 megahertz, okay, fortunately it only takes 25 milliseconds to reach that error condition. So now that we know that we can reproduce the issue, we know approximately where the problem occurs. We can set up the debug technologies, okay, to accelerate the point of interest. And then what we can do is we can actually look for states prior to the lockup condition. So what we saw first time round is at the cycle count, we got a value via the UART. And then what we can do is to set up the fastest on-chip VRAM to actually trigger, okay, 50,000 cycles before that point. And then what we can do is to enable the high capacity deep trace debug and the global state visibility in order to capture around that point of interest. So with the global state visibility, we're going to capture 100,000 cycles. This is set dynamically. At runtime, we can capture more over periods of time. But what we're going to do is just to actually give us a pre-event trigger and start capturing via the global state visibility for 50,000 cycles before that event, so that we capture around the point of interest. But from that, once we've actually captured using the GSV, we can actually download it. We can actually create a fully contained debug environment. In the Verdi environment, we create databases. These databases will contain the original RTL. They'll contain the activity, the FSDB file that's been captured from the actual prototype system. But we also have databases just letting Verdi know, okay, all of the optimizations and all of the transformations that have been made between the RTL compilation and the actual bit file generation. What this means is that we can actually generate these fully contained databases, and we can actually export them as a fully contained package. And it might well be that we export them to a number of different users that will want to debug it. They could be anywhere on different networks, anywhere in the world. Okay, and then each of the users would go forward, obviously with the knowledge of the design and any information to hand, to go to look forward to debug it. Now, what's interesting here is that with the HAPS 100 platform, we do capture the sequential state, but Verdi has the ability to actually build the or to show the signaling between the sequential states in something that we call waveform expansion. It means that the user has generally got full visibility into the DUT operation. They can actually see what's going on in the RTL. They can correlate that to the waveforms, and then correlate that to the actual hierarchy of the design as well. Okay, a bit more detail on that debug environment. So what we have here is that we got the on the bottom, we've got the waveform that's been captured from the DUT operation. You can actually see the point of lock here, where the AXI transactions appear to stall. And then we can actually correlate that in terms of RTL signaling, and we can actually see where that would appear in the DUT itself. So as a summary, okay, what we've shown you here is how we can actually look to find hidden bugs in deep cycles. using the ZeBu Server 4, the HAPS 100, and the Verdi environments. So ZeBu Server 4, very high capacity, very strong debug capability with DPI monitors, stimulate replay, and fast readback. HAPS 100, highest performance FPGA prototyping. We've got the deep trace debug with the debug capabilities, and we've got the global state visibility in order to capture, say, the complete state of the over many cycles, hundreds of thousands of cycles of operation, right? But most importantly, or as importantly, is the Verdi environment. Okay, both the ZeBu and the HAPS platforms are fully integrated into the Verdi environment. All the databases that are extracted from these platforms can be fed into Verdi to give the user a complete debug environment at the RTL level. So with that, that's the end of our presentation. So I'll open up for questions now. Thank you. So do we have any questions for myself and Youcef?
I don't know. Maybe we can wait a little bit.
Yeah.
I could maybe still share the slides if you want to come with more questions, I would say. You can also use the chat if you want.
Okay, so no questions? Okay, Youcef, I think we're done. So thank you everybody for listening to us today, attending this this session. Again, I apologize for the power outage and my absence for a few minutes in the middle. Youcef, anything?
Thank you, everyone. Yeah, thank you. Aidan, do you want to add anything? Or hold on.
No, if you don't have any more questions.
You have a question on the chat. What are advantages and disadvantages of ZeBu technologies versus FPGA prototyping? I can give a start as a question. So, I mean, a start of answer. So as we can see here in the summary, I would say the advantage of emulation is that you can integrate a huge system. I mean, big designs. Yeah. And I would say, debug technologies is, I would say, faster, but the goal with the emulation, the initial goal with the emulation is really focused on the duty. Here on the prototyping platform, I would say you cannot get design as big as what we can have here with multi-unit ZS4. I mean, not yet, but the focus is maybe on software development.
Let me add to that, Youcef. Yeah, so you're right. I think they are complementary technologies. Okay. You know, so ZeBu is very high capacity. Okay, it's got a very, very strong debug capability, as Youcef has described today. FPGA prototyping as generally it will give you higher performance. Okay. Also, prototyping leads itself to real world interfaces. So if, for example, you want to actually integrate with a PCIe or USB, you can actually do that on the HAPS platform. You can get some real world daughter boards, PCI links in order to validate those real world. So I'd say that they're both complementary technologies. The ZeBus will run tens of megahertz. The HAPS can run, multiple tens of megahertz. So it could well be that you would use the HAPS to get to a point of interest, which could be many days, a bit quicker. But the depth of the debug technologies and the, as Youcef has described, okay, I would say it's more comprehensive on ZeBu. I'd also say that the ZeBus have a very strong power analysis technology as well. I hope that answers the question. Okay, any more?
Maybe we can wait 2 minutes more. I don't know.
Okay, I think we're done. Okay.
Yes.
I think that's okay.
Yeah, I think people can still contact us offline. I mean, if you guys have any question or please feel free to reach us.
Okay, thank you, everybody.
Yes. Thank you, everyone. Aidan.
Have a great day, everyone. I'll take it from here.